Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about flywheel synchronous condensers. So let's dive deep into it. So what exactly is the problem here? Well, problem is that we are adding more and more renewables. Now, the reason why we are adding it is simply because it's cheaper. Coal power plants gets more and more expensive to run, not only in terms of water consumption, but also in the fact that coal gets more expensive. Let's not even go in the oil. So reality is that we want something that is cheap and abundant. Thankfully, solar and wind does supply that. So everybody's doing it. It's not fancy. It's not nothing to do with environment. It's cheaper. Nothing more than that. And it is powerful, it is abundant, but it has this one issue. Now you were like, okay, it does not work 24 into 7. You do not have large enough network. If you have large enough network, 24 into 7 is doable. And we have energy storage system that can take care of the rest part. And again, thankfully, because of nuclear technologies and nuclear fuel in 1930s, we have a solution for that can work in gigawatt hour scale. So that part is sorted. Energy part is sorted at this point in time. However, we do not have grid inertia, meaning we did not plan for it. And you have to understand, solar panels started with watts of power, like 1 watt, 10 watts. You remember the old watches? So that's how it started. So we were like not serious about it. Heck, as early as year 2000, if you have told anyone that whole world would have hundreds of gigawatt of solar farm, they will have laughed at you. Like as early as 2010, even in India, if you had talked to someone, it's like, yeah, we're gonna have every year we're gonna add a multi-gigawatt of solar farm. They're like laughed at you, but that is happening right now. Why? Cheaper. But the solar is not designed for that because it does not have grid inertia. So let's understand the core aspect of how the heck we can turn on anything and turn off anything without voltage and current going kaput. Well, simply because we have frequency. What is frequency? Frequency is the one good benefit of AC current, that if you have a spinning mass like this puppies, they spin. So they have a big, massive mass that is spinning a generator. So what happens? Let's just say you are a steel mill and you have a ginormous draw, which we call arc furnace, or let's say inductive furnace. In those sort of things, you turn it on and it can drain bonkers amount of power, like 100 megawatt or more than that. So you have something like that. What happens when you turn on the switch? Well, it leaches the power as quickly as possible from the nearest transformer, which is connected to. What does happen inside the transformer? Transformer low side leaches the energy from high side. High side, where the heck it leaches the energy from? It leaches from the substation, and it goes back and back and back and back, and it reaches the final generator, whichever generator is the closest. So it reaches there, and then it leaches energy from there, because energy cannot be created nor destroyed. You were running this on a fixed load, so what the hell will happen? But here's the funny thing. Ironically, because our early technologies were not that efficient, we used to have to make them very bonkersly heavy. It takes time to slow down. For example, if this puppy was rotating at 1500 rpm or 3000 rpm, it's not gonna go from 3000 rpm to 0 rpm because you dumped 100 megawatt of load. It will take time to slow down. How much time? Enough for control mechanism to detect that something is happening and react to it. That's the whole point of grid inertia. Give enough time for basically compute mechanism and control mechanism to look at it. Basically, your spike that you dumped in your induction furnace could be, but spike that your generator is gonna experience is like, it's slow enough where it's like, okay, that's what's happening. So what does computer do? Well, in the old days, there would be a governor will detect, hey, RPM is getting a bit low because you're leaching energy from it. It's like, whoa, increase the steam flow to compensate for that. And same happens backwards also. Let's say you had the same steam furnace, steel furnace working, and then you turn it off. Why wouldn't you have like ludicrously high voltage running into your system? It won't, simply because now you stop leaching the energy. But again, you have higher steam pressure here. It's spinning at expected load, but that load has been removed. What happens? Rotor is now free. It does not have the magnetic resistance that was designed for it. It was like, bro, the resistance disappeared. Basically, the brakes failed. So it will start to speed up. But again, it is hundreds of tons in sometimes. It will take time to speed up. Time that is long enough where steam valves will be like, brah, it's supposed to be spinning at 3000 rpm, it's starting to reach 3100 rpm, starting to reach 3105 rpm. It's like, yeah, cut the steam flow. And again, that's just one variable. There is another variable. Basically, the rotor of the generator has current going into it. That current is generally first controlled before you control the steam, because steam takes some amount of time to couple, and current that is in the rotor is far quicker. So that's how we have spinning mass, and that's how we stabilize everything. And this is the key aspect of it. Now, again, if you are in America, put this by 60. You are in everywhere else, it's 50. So 50, normal, everything is good. What happens if you remove loads? Let's just say we have a lot of solar, duck curve happens, and the RPM will start to go up. Consequence of that would be frequency starts to go up. So if it crosses 50.1, it starts to reach what we call yellow limit, meaning things are reaching serious level. People will start to pay attention, phone calls will be made. And then it goes from 50.2, it's like, whoa, whoa, whoa. Computers will start to react at that point in time. At that point in time, you have to cut power, meaning every country has the rules and regulation, and those regulations are like not very tight on terms of voltage. They're like, yeah, low voltage, high voltage, you can handle it. They are very tight about frequency. So they're like, yeah, the moment it starts to cross, let's say 50.5, it's like, yeah, you have to cross the legal limit, so you have to cut the power, meaning substations, SCADA system will be like kaput. It will start shedding load. And then if you keep going higher, let's just say you're still overproducing and it crosses 51%, this is red alert. The moment you start to touch 52%, generator will start to trip, because that's the last line of defense. Generator has to cut power. So generator itself has a basically circuit breaker, not the substation circuit breaker. Generator itself has that. Those were set to generally trip at 52. And what happens if it goes even further than that? Yeah, total blackout. What does total blackout mean? Yeah, grid has lost inertia, meaning you have to start all of them one by one. It could take days. That's not something that's like a circuit breaker. So no, you have to start a power plant. So that happens when you have too little energy draw and too much production. Opposite also happens. So let's say you dropped, basically you're starting to put load and more load into it, 49.9. People are like, whoa, whoa, whoa. People will start to pay attention to it. It starts to drop to 49.8. It's like, yo, figure out where we can get extra power or load shedding. People will start to make phone calls. It starts to reach 49.5, legal limit. You have to shed loads. You cannot send dirty power, especially to high priority targets like data centers, hospitals, things of that nature. You cannot send dirty power. And then it starts to reach dangerous zone, which is 49 hertz. Yeah, red alert. You are very close to generator auto tripping. And then 48, same thing, total blackout. So how the heck we know grid works? Because of this. This is the one core benefit of AC electricity. And if you look into any control room of a nation, how the heck they're controlling the electricity? They have a giant monitor that shows what is the frequency. Again, I could not find the UK has a system where they have a very nice graph, like a rainfall kind of graph, where it's like, what is the frequency? So we do try to make it as close to 50 as possible. But again, physics does not allow absolution. So it's like, now it is very tight, but that's how we keep everything stable. And it requires inertia. It requires massive object spinning. The more the massive, the more stable the grid becomes. Because again, if you have 100-ton object spinning and then you jerk load into it, it will it will notice it. If you have 600-ton, it's like, bruh, I ain't got time for this. So fundamentally, that's what you want. Like induction spike will happen like this, and you want your generator spike to happen like this. The slower it is, the better it is. So you want mass, and that mass has to be spinning. So it's actually coupled. So that's the core problem. And yes, if you start to directly dump a lot of solar, a lot of wind into grid, you will kaput the grid because it will have too much power, but not adequate amount of mass. So this will start to go like this, and generators will trip left and right. So basically your whole substation grid will be like, no, blackout. So let's look into the solution. Solution is synchronous motor. Now let that be clear. Synchronous motor is the hardware. If you run it in certain way, it becomes synchronous condenser. So we are talking about motor first. Condenser is its mode of operation. So AC motor with synchronous speed, meaning if you know about basically induction motor, you know for a fact that if magnetic flux is here and pole is here, pole will never be exactly lined up. Pole will always be chasing it. That's how you induce induction. So it fundamentally has what we classify as slip. Now based on the load and voltage and all that, the slip would be low or high. Basically slipping far or slipping less. But again, in a synchronous system, it's locked. It's like completely locked. So it is more efficient if you can completely lock it, aka reach synchronous. It is very efficient, but again, induction stops working at that point in time. So you have to have a different topology. So hertz is locked to the RPM and you basically have zero slippage. That's awesome. But how would you do that? Well, you can have two options. Basically, you have to have magnetic field in the rotor itself. So we generally put rotating electromagnet inside, meaning stator is an electromagnet. Same way, rotor is also an electromagnet. So once you have that, but again, that creates a problem. How the heck you put power into something that is spinning? So you utilize two options. One option is slip ring. So you will see giant power plants have slip rings. So slip rings is where you dump energy into it for rotor, and that's the first line of control. So generally steam valve is like, if a lot of fluctuation is happening in the RPM, then steam valve. Generally all the frequency control will happen on this level. Those fingers are like, whoa, 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 too much power, too little power, too much power, too little power. That's the management, hundreds of times a second is happening on those puppies. So, and again, you're like, why it's brushed when we have brushless option like this, which we call exciter option. This has much tighter control loop, meaning if you want to tightly lock the frequency, this is your guy. This is awesome. But it does have the penalty that it has to be a stable system, because those brushes in power plant structure, they do not have amps going through it. They have kilo amps going through it. And again, some of designs have thousands of kilo amp. Let that be very clear. Those puppies are huge, meaning if you have a minor deviation on the bearings, it will not create arc, it will weld it. So fundamentally, those things require very precise precision. You cannot just lull it. So if you have a scenario, let's say hydro dam, where you have water vibrations and all that, people may be like, yeah, let's not risk it. Let's just put a exciter there. What is exciter? Exciter is very simple. You have an electromagnetic coil around the exciter and you send AC frequency into it, and tada, AC jumps into the rotating part. Then it has, again, it's a AC, but you need DC electromagnet here. So what you do, you have what we call spinning diode. A diode takes the AC, converts it into DC, and tada. And again, you still have the same control, because here you can have auto voltage regulation, you have control system here. You're like, okay, how much we have to do? Does it work? Absolutely, very flawless system, does work. Many hydro dams use it. It's an awesome system, but it does have slower control loop compared to slip ring. So these two are technology I utilize. But if you utilize what we call exciter topology, this puppy, it becomes perfect motor. Like, there is no motor that is even half as good as this puppy. It is brushless. There is no friction of the contact surfaces. It is magnetless. You're no longer begging to China. It is synchronous, meaning it is efficient. For example, if you look into magnet motors, magnet synchronous motors, those are really good when it comes to torque, where it's like, that's really good, especially at low RPM. It's like, I got you, fam. Now, then why does some motors have induction? Well, inductions are really good at high RPM. So if you want a basically system that is designed city driving and you just want a lot of 0 to 60 kind of speed, awesome, magnet is awesome. But if you want a 0 to 200 kind of speed, it's like, yeah, bro, induction motor is the fam. So, and again, there is other option also, for example, which you call reluctance motor. So people generally try to create a basically hybrid children of these, where you have reluctance and then you have magnet assisted reluctance motor. So you're trying to compensate for those. This is like, I do not care. Why? Well, it is an electromagnet, meaning you can control its magnetic flux, meaning at low RPM you can increase it. So it's like, I got this. And high RPM, so back AMF is not becomes an issue. You're like, start to tone it down. It's like, bro, easy, easy. So it's a perfect topology. That's why majority of electricity that you're consuming right now, if it's not coming from solar or wind, it's coming from these puppy. And yes, motor and generator is the same thing. So it's very perfect. On top of that, this has the ability that the fact that you can send current into it, you can change its VA rating, meaning how much energy is consuming. It's described in two systems, especially in AC currents. First, you have watts. Second, you have volt amps, basically power factor. So this puppy, again, I have linked this video down below. Please watch it. It will blow your mind. That induction motor, we all know induction motor. It's awesome. It's robust, but it is naughty as hell when it comes to electricity. It messes it up. It has a very bad power factor. So this puppy, you start it, it acts like an inductive load, like every motor. Cool, awesome. But here's the deal. You have the ability to control energy that is going into the rotor. What if you increase it? It will start to reach resistive. Let that sink in. You have a spinning thing that is spinning. There is no brush, there is no magnet, and it's acting like a freaking resistor. That's why all power plants utilize these sort of motors. Whenever you are talking about large industrial load, generally they do not prefer induction motor for this exact reason. If you reach this and you reach a resistive load, it's easy. Your power factor is 1. Your transformer is like, chill. And again, by the way, for commercial players and industrial players, they have to pay for bad power factor. So having a motor that's like, I got this, there is no power factor issue, it's like, awesome. And here's it. On top of that, what if you still keep pumping energy into it? This jumps from resistive to capacitive. And now we come to the fact that why we are calling it condenser. Back in the old days, capacitors used to be called as condenser. So this can jump from inductive, resistive to capacitive, and it's controllable variable. So back in the old days, before capacitors became robust and reliable at 50 mains signal, we used to have motors like this spinning. for giant factories. Like, what was the point? It was acting as a synchronous condenser, meaning based on the power factor, it will control its rotor current, and based on that, it will compensate for the system, meaning your transformer that is actually leaching energy from the system, it can get one power factor. It can be done. It has been done. It used to be done. Now we no longer need to, because we have much better, robust capacitor system. But again, if you want something smooth, old school, works for 70 years, this is the thing. So that's the core aspect. The fact that you have a electromagnet in the center, you can switch between all three modes of operation: inductive, resistive, and capacitive. Meaning, if your power plant basically consumers, they are like, bro, we have chill, everything is nice, everything is good, you can come to resistive level. It's like, then some power plant is like, nah, bro, what if we melt steel? Inductive. It's like, whoa, 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 whoa. You can compensate for capacitive load. So it can react to it real time, quite efficient. Really awesome system. Please watch the video. It will blow your mind. You can go from inductive, resistive to capacitive. So what are the pros of this configuration? Well, it's mass. At the end of the day, it's a mass, and few tons to hundreds of tons is possible. So this mass is spinning. Now here's the deal. It's not grid frequency. Let that be very clear. It's not creating its own grid. It's syncing up to the grid. For example, you have a power plant that is creating power, and you have ginormous solar farm. So power plant only has inertia of, let's just say, equivalent of 100 megawatt. But again, your solar farm could be huge. Like in India, 2 gigawatts or 10 gigawatt or 20 gigawatt. But here's the deal. You can't have 20 gigawatt of load on those tiny inertia. It's like, bro, it's out of scale, out of proportion. But you put this will not create its own signal. It will take the signal from a power plant, that is the source, and it will amplify it. Meaning, it's like, I got you. It's like, I got you. So all this extra solar we are adding proportionally enough mass to it, inertia to it, that it will work. You will no longer have the fragile grid problem that you used to have. So that's the core benefit of it. That's why everybody is going back to this technology. So it's not a frequency source, it's a booster of sense, so to say. And it has inertia that responds to basically whenever you have power changes, fluctuations, all of those puppies is like, I got you. It does that. Now, it works in millisecond time frame, meaning when you have frequency going up and down, the solar farm is generally followed by what we classify as grid tie inverters, meaning they are also expecting a signal. But again, how can you expect a signal if you are the source itself? So this becomes like, locally, as in like, this is like, I got you. I will simplify all of that. I will boost the signal, so you all of you can sync to me, and I will sync to the outside grid. So in a millisecond frame, it's like, instead of fluctuating like this, which again puts a lot of strain on your inverters and very serious risk of what we call cascade failure, meaning most of the grid can just go block out. So in milliscale time frame, it's like smooths it all out. And then if you're like, okay, that's not good enough, right? You need a bit more oomph, especially if you are talking about bonkers solar farm. Then you add flywheel to it. It's just same motor, you just add a flywheel to it. At that point in time, you get what we call a ride through. You have to understand, grid are designed to take a beating. Because again, you will have lightning fall. When in the versus small scale, nobody cared about it. Now you are the source, you care about it. That lightning fall happens often, and you will have minor issues often. You have to ride through it. You cannot have a scenario where it's like, oh, some fault happened in substation and a whole solar farm got disconnected. It's like, not good. Again, you have to have ability to jump through minor inconvenience. So how do you jump through? Well, flywheel. It gives you what we call a ride through capability. Some of them can ride through almost few seconds of blackout. It's like, it can handle that. It's like, which is magical. Be mindful, before this, it was like, yeah, grid will become very fragile. Now it's like, I got this. The bigger the flywheel is like, I really got this. Heck, this can have enough flywheel mass. If you can add, as long as you can start spinning it, keep adding to it as much as you want. If you have bonkersly heavy mass, you can have like bonkersly robust ride through system. And it also boosts short circuit current. Now, like, wait a minute, why that's a good thing? Well, because you have to understand, our grid was designed, aka substation circuit breakers, all of them are designed for giant short circuit currents. They expect short circuit current, only then it opens up. If it's not giant, it will not care. And that's the biggest fear of solar systems. And again, wind also. If you have minor issues, it can creep through a larger and larger substation, and by that time it will have to be kaput a large sector. Basically, your country could have minor solar farm issue, which is like minor issue. It will become kaboom by the time it's reaching a large substation. It's like, yeah, I have to isolate this whole sector because now the current is big enough. You want surge current, basically short circuit current, to be very fast. So substation is like, whoa. You need that because substation is designed for that. So this is a very good thing. It acts like a, for short duration, it acts like a generator because it has so much mass to it. It dumps all that energy. So basically it guarantees that all the substation safety systems will engage. It's like, nah, you will not let this pass. You will stop it. So it's awesome. And power factor correction, again, you have rotor current control, power factor correction, inverter becomes easier, everybody's life become better. And fundamentally, it's nothing complex. It's ancient technology. How ancient? Well, from 1920s, we have been using it. Again, the synchronous motor is even ancient. By 1920s, we started to utilize it as power factor correction. Nowadays, you see basically capacitor in substations. Back in those days, we used to have condensers. And again, condensers made a very huge comeback when people realized DC current is the best for long range transmission. So we used HVDC. But again, they had the same issue. It's like, dude, you dumped, let's say, China's three gorgeous dam dumps 12 gigawatt of power. Awesome. You transmit it over 12 kilovolt high voltage DC. Awesome. But here's the deal. You have the power. You don't have the grid inertia. And the substations there and the power plant there, while they have the inertia, that inertia is not proportional to 12 gigawatt. It's like synchronous condenser is like, I got you, fam. I got you. You spin it. Basically, it takes the AC signal that is there. It amps it up. It's like, I got you. Now I am stable for 12 gigawatt. So HVDC also use that. These are from America. This is from HVDC system. So HVDC also uses it for stability. Now, how can you make them better? Well, it is a motor, it is spinning, so you have options. First option is making the axle, basically rotating mass floating. You can have magnetic bearing, air bearing, whatever your choice. Or to improve the efficiency, you can have superconductor also. And yes, we have built it, have used it. It's ancient technology. So these are the pro about it. Nothing fancy, no PID loop of like, grid forming inverter, which is a black box magic technology. Again, I'm talking about it as a black magic simply because, yes, I do understand the system. It's silicon chip. One bad bit flip, you can kaput the whole system. This is like robust, bro. I'm done. Wind tested. Like there is no discussion about this. If it faults, you did something wrong or it was manufactured wrong. There is nothing about this that is untested. There is no discussion here. It's like, it will work. The end. So are there any consequences of this? Yes. The biggest consequence is this is unfortunately not the source. The only way where you can make this a source is like you have to be very inefficient. But again, if that is the requirement, you can deal with it. You have a giant motor that is spinning this as a generator. So you have a motor, you have a flywheel, and then you have a generator. So basically, solar farm puts power into the motor itself. It's acting like its own grid, and then you create a generator. That time it can do black start. Not recommended, never even needed, but that's an option. So it is one thing you have to understand. This boosts the signal, does not make the signal. It is very critical aspect of it. So it's not designed for what we classify as black start. So it is messy in that regard. Another is it does waste power. You are talking about a ginormous motor that is going. So it is power hungry, so to say. It can waste few percent of the power, of the total power. But again, without inertia, the grid falls. So people are like, yeah, that's like no bueno. That's not an issue. But again, it is a mechanical component, so you do require to do maintenance on these puppies. So in solar farms, solar panel only require cleaning, and we have robotics for that. Yes, India has a lot of solar farm, and yes, we have a lot of robotics that cleans that. That's done, sorted. Inverters, we rarely have to touch them, but this you do have to touch it regularly, maintenance wise. How regularly? It's exactly a power plant generator. So if every 5 years those puppies have to be touched, so this puppy will have to touched every 5 years. So that is there. You have to increase your maintenance cost. And it is very big to ship, meaning if you have to transport it by road, you will know the pain. And many times the transport itself would be more costly than the damn engine. So yeah, it is expensive. Although Europeans somehow have brain and they started to like, hey, wait a minute, we have so many coal power plants that we have to shut off either because of lack of water or because of higher cost of coal. It's like, what if we converted that generator, turbo generator, and just add a flywheel to it, change the electronics, ta-da! It's an inertia system, ta-da! They did it long ago. They were very smart. They're like, yeah, we have so much wind power, coal does not make sense, but we have the stuff, why not use it? Why not solve the wind's issue instead of like throwing away the stuff? It's like, hey, we already built it, plant is there, generator has already been shipped there, just ship the basically flywheels, done. So there are certain cons to it. So what can we expect in the future? Well, first thing you have to understand, we do need some source power plant. For example, let's say I go all in, 100% renewable energy. Can it be done? Absolutely, without any issue. It's just a matter of time. Why? It's cheaper. But you would need something that can give you that initial signal, because once you have that signal, you can keep boosting it. Every solar farm can boost it, and then you're like, don't care about it. But you do need that signal. So where do you get the signal? Best source, renewable source, is biogas. I do not consider a hydro dam a good system, because again, it fries the rivers, and India is running low on those. China is running low on those, so not recommended. Heck, even Hoover Dam is like, bruh, I think it's very low, 35% fill at this point in time. That's also not swimming in money or water. So biogas gives you the ability, you can turn biogas into steam or jet engine, but again, steam would be better, because again, steam systems are huge. You want inertia signal. So biogas is a very good system, long-term, sustainable, awesome. As long as human, there is poop, there is biogas, chill. So that part is there. And energy storage for power plants. This is like what Europe is doing, where it's like, hey, old power plants, why not convert into battery? India is also doing it in Asansol. Basically, we have graphite blocks. Those absorb heat during the charging cycle, dump heat into steam during discharge cycle, and tada, you get grid inertia. Pumped hydro, awesome. During charging, it does not provide inertia, but during discharging, it is a hydro dam. So you get full inertia. You do not have to worry about it. So that's the whole point. And there are three whole sectors that love this puppy, which is solar for India, wind for Europe, HVDC for China and Europe and India. I have no idea why the heck USA is so behind in HVDC, but it is. So all this puppy need this. And it can be very simple, there is just a dumb motor, giant motor, or it can be complicated, where you're like, okay, what if we have superconducting? What if we have floating system? I think floating would be more beneficial rather than superconducting, but again, I have not seen that many superconducting one. Few, like this one I think is superconducting one, but not that many. But floating bearings I think would be far more desirable. And the more massive the flywheel, like this is the European one, where it's like giant country. I'm pretty sure this puppy is almost 20 or 30 tons. Massive puppy. So the more bigger it is, the better it is. The bigger route right through you will get. And all thermal plants are already there. That's the best part of it. It's like, hey, we have this system. We have people wanting a job. It's there. Keep using it. We have the substation. Keep using it. We have the control electronics cabinet. Keep using it. We just have to disconnect the steam turbine and put a giant flywheel there. So it's not that. And again, E2S power design that they are working, they are using the steam cycle also. So you do not even have to worry about it. So that's awesome. And it's a great technology for electric car also. Now, like, okay, if this is great, why don't we use it? Well, we do use it. It's a company that they have already made it, and it's already in few cars. It's just that magnets were cheaper. And again, Tesla's first car did not use magnets. They used induction motor, 20,000 RPM induction motor. So it's not an issue where it's like, oh no, we have to have magnet. It's just that magnet gives you low RPM performance, and other things gives you high RPM performance. This is like, it gives you both. And magnet price had to reach enough where other companies are like, yeah, I do not like the idea of begging to China. So that has happened. So when I originally covered a magnetless motor, that was like one company was announcing it, Miele, I think a German company. Now there are 3 OEMs, all are selling it out. So that's done. So this is an awesome technology, like ancient technology from 1920s, and we are like, yeah, we got this. So if any Tom, Dick and Harry tells you, oh, the grid will not be stable if you have, like, renewables into it, take a slipper and bitch slap them. It's a solved problem. Like how efficient you want to make it, how cheap you want to make it, that's up to you. Converting old coal power plants, I really support that idea. We have the carbon footprint of those puppies. Why not use it? So this was my presentation on basically flywheel synchronous condensers. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excitement. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.